relative speed, or, and this is going to be your trigger, you know you're going to use relative speed if there is more than one moving object. And you asked, or you said, because relative, the reason Einstein called it relativity is he's really asking, what if two objects are moving relative to each other? What are the rules of the universe then? Okay, so your trigger, you'll know, oh, we're in, especially at the end of the year on your final, once we've learned a whole bunch of physics, you'll know, oh, there's two objects moving at different speeds. That's going to be a job for relative speed. I'd like you to imagine that you're in a car driving on the freeway at exactly 100 kilometers per hour, and a Ferrari goes hurtling past you. Its speedometer reads 180 kilometers per hour. And there's also a tow truck parked on the side of the road. Its speedometer reads 0 kilometers per hour. We want to ask ourselves, what would a person in each vehicle, how would they see the other vehicle behaving? So suppose the tow truck was parked at rest. What would the tow truck see? This isn't very profound. This is sort of how all of you think. What would the tow truck see you traveling relative to the tow truck? Well, first of all, the tow truck would see you traveling at what speed? What direction? If we want to make it a velocity, well, when you're behind the tow truck, it would look in its rear view mirrors and it would see the headlights getting closer. And when you're in front of the tow truck, it would see your tail lights retreating, and we would call that forward or positive. That's how we decide which way cars are going. We look at the taillights and the headlights and ask, are they getting closer or further? So the tow truck would say positive 100 kilometers per hour. And cool, same with the Ferrari. The tow truck would see the Ferrari traveling at 180 kilometers per hour. And that's kind of, well, duh, because that's the velocity that most of us are used to when we're comparing a velocity to something else at rest. By the way, are you all at rest right now, technically? Why? Okay, Earth is spinning and moving through the solar system, and the sun is moving through the Milky Way, and the Milky Way is moving through the universe. It is all relative. It really is. But, okay. The more interesting question is, what would you see? Let's first of all talk about the Ferrari. How fast would you see the Ferrari traveling relative to you if 80? Would you see the Ferrari traveling forwards or backwards? Let's use our imagination. We would see the Ferrari in the rear view mirror's headlights getting closer. Once it passed us, we would see its taillights retreating in the distance. And what direction, Owen, would we call that? And so, yeah, we would say the Ferrari is going relative to us. And you may have noticed that on the freeway, especially if you're going fast and the car beside you is going at exactly the same speed, you can look across and, oh, relative to us, they're at rest. What's the correct answer? Yes. They're all correct. It all depends on what you choose to use as your frame of reference, but then you can do a consistent law of physics from whichever frame of reference and get consistent rules. What would the tow truck be traveling at relative to you? Well, its speed, the tow truck speed would be 100 relative to you because you're traveling at 100 relative to the tow. What? Why negative? Because you would see when it was in front of you, its tail lights coming towards you. And when you passed it, you would see its headlights in the rearview mirror going further away. So now we got to use our imagination, Cleo. If you imagined that your car was standing still and the earth was just spinning underneath its tires, the tow truck would be traveling backwards. Is that right? So negative. And at 100, because that's the speed difference. Now, I'm being a little fussy, Noah, right now about direction, negative and positive. We're going to ditch direction in a little while and just talk about relative speed because that's really what we're going to be interested in. So we're not going to worry about negative and positive too much, but it's a nice thought experiment. What would the Ferrari see? Well, how fast would the Ferrari see you traveling? Oh, I thought you had your hand up. Sorry. First of all, as a magnitude, 80. Direction, yet negative, because the Ferrari would see you backing towards it at 80 kilometers per hour, and then it would see your headlights backing away at 80. As far as it's concerned, that's what the universe is doing. And the Ferrari would see the tow truck traveling at negative 180 kilometers per hour. I wrote, Mr. Dueck, is there a short way to write this? You'll notice I typed VU relative to the tow truck, or V Ferrari relative to the tow truck. There is a shorthand notation I'll introduce you to. There always is. So if I wanted to write V Ferrari relative to the tow truck, you could write V Ferrari relative to the tow truck, or you could write it like this: the velocity of the Ferrari relative to the tow truck. The first thing goes first as a subscript. An arrow means relative to, and what you're comparing it to goes last. What you're using as your frame of reference goes last. Yep.
So would you be able to use, instead of velocity, would you be able to use weight, and then like for different planets relative to like Mars, let's say?
I can't answer that question because you're using the word weight incorrectly in a physics term. Mass, which is very different from weight. No and yes, because I haven't yet told you how mass behaves under relativity. The answer is it does weird stuff. So here's the point. As far as you're concerned in the car, you really don't see the Ferrari traveling at 180 kilometers per hour. You only see it traveling at 80. And it only sees you traveling at 80. I don't care about the direction. The relative velocity of any moving object depends on your point of view. The fancy word is your frame of reference, your reference frame. You see the car moving at 80 kilometers per hour, but the other driver sees you moving backwards at 80 kilometers per hour. The difference is 80 kilometers per hour. I'm not going to be too freaking out about the direction in just a bit. But let's look at a couple more. You might have experienced this if you've ever walked on a moving walkway at an airport. Anybody walk on one of those moving walkways before? Right? And you get kind of a weird feeling because you're walking slow, but when you look over the railing at the ground, your brain is going, this somehow doesn't feel right because my legs are moving at a certain speed, but the ground is moving faster than I'm used to. It's kind of a, giggly little, like they're kind of fun. Okay. A classic thought experiment is a train with a person walking on it and an observer on the ground. So here we have the train moving to the right and the person walking to the right. What would the person on the ground see as the velocity in this first situation, magnitude and direction? And my abbreviation for the relative velocity is I usually just write V rel. You could write V ground relative to whatever. What would the magnitude of the velocity be that the person on the ground sees the person on the train walking at? I'll give you a hint. It's neither 1.2 nor 15. Owen. Direction. I'm going to say to the right since we have a picture this time. But yeah, positive. What about in the second situation? What would the relative velocity be? Direction. Yeah, still, I mean, the person is facing to the left. It would look like they were kind of strangely somehow moving backwards while walking forwards, but okay. Just don't write this next bit down, but as a thought experiment, what if we put an Olympic sprinter on the train and the Olympic sprinter was running at 15 meters per second that way? What would the relative speed be to the person on the ground? As far as the person on the ground is seeing, the person's at rest. Their legs are moving, but something weird's happening. Does that actually work? You have to go early? Oh, you're just packing up your binder? Does that actually work? Put your pencils down and look up. Let's kill some animals, so to speak. Actually, it's this little dance that we're going to talk about goes on in nature all the time, and it's remarkable how herds of animals can do this math instinctively. A zebra is running away at 50 kilometers per hour from a cheetah going at 90 kilometers per hour. What velocity does the zebra see the cheetah as having, and vice versa? First of all, what's their relative speeds relative to each other? Just give me the magnitude. We're not going to freak out about direction. How fast do each of them see each other traveling? 40. Okay. So I'm going to say the velocity of the cheetah relative to the zebra, the magnitude is going to be 40 kilometers per hour. Now, the zebra, if it had a rear view mirror, would see the front part of the cheetah getting closer and closer and closer and closer. So I think as far as the zebra is concerned, the cheetah's running forwards. What about the velocity of the zebra relative to the cheetah? Same magnitude, Carter, of 40 kilometers per hour, but the cheetah would see the hindquarters of the zebra getting closer and closer and closer. As far as the cheetah is concerned, the zebra is backing up, right? So negative. I like question C, I like question C, I like question C. Question C is a nice question. Davis, what's question C? Where's my seating plan end up, by the way? Has it made its way around? Giovanna, behind you? Thank you. Here, we filled it out. Lovely. What's this question asked me to find? Part C. Time. Now, I mentioned this before I started the video, but now I'll say it again for the video. In this unit, we're always going to let A equal 0. We're not going to be able to deal with acceleration when we start looking at Einstein's special theory of relativity. When you bring in acceleration, that leads to the general theory of relativity, and the math goes crazy. So for these questions, when there are two objects moving at the same time, what's A always going to be? 0. So let's even write that down. A equals 0. Oh, and time equals question mark. What's that 90? Yep. What's that 40? And I don't care right now about positive or negative. You know what? Time's a scalar, so let's just use the positive values. What's that 40? What are the units next to that 40? So it's a velocity. 40 what? Do I do physics with kilometers per hour and with meters in the same question? We need to convert 40 kilometers per hour. Well, no, we're not going to round off because we're going to use this to find a better answer. If anything, I'm going to use my answer button, but I'm sure as heck not going to round this to 2 sig figs along the way. Correct me if I'm wrong. Isn't it 11.1111111111? And I would say go 40 divided by 3.6 on your calculator and just store it there. Which equation? Put your pencils down, look up. Technically, look up. Yeah, you look up. Aiden, look up. Thank you. Look up. You too. Okay, is everybody looking up now? Technically, I would use this. But Cleo, what's A?
0.
Right? And then, what's A?
0.
So do you know what VI is? 11.1. Do you know what V final is? 11.1. Do you know what V middle is? 11.1. Do you know what every single V is going to be if there's no acceleration and we're traveling at a constant speed? So we often don't even bother putting the initial. In fact, what I'd like you to put there instead is VREL T times T. So let me put all that together. We're still using D equals VI T plus a half AT squared. But if two objects are moving, what did I tell you A is going to be?
0.
So it becomes D equals VIT, except are two objects moving? This is a job for relative speed. D equals VREL times T. Austin, what am I trying to find? How would I get the T by itself? I had a whole bunch of you on the test. There was a question that involved echoes and sound or something like that. And I had a whole bunch of students do this. T equals V over D. Sloppy mistake, I'm going to say. Because, and if you're not sure, go systematically. What's going to drop down like a domino? Talk your way through it. The D will. And then I want to get the T by itself, so I'm going to move stuff away from the T. What's right next to the T? The V. How will I move it over? Well, what's it doing to the T? Multiplying, so
Right.
that equals T. Yet another equation. I wouldn't memorize it. Use your answer button. So you're going to go 90 divided by, I'm going to write 11.1, but use your answer button, please. And I think it works out like evenly. That's why I did that on purpose too. Okay? Units. So here's how this works in nature. If safety is 8.0 seconds away, the zebra lives. If safety is 8.2 seconds away, the cheetah eats. And it's amazing, if you watch nature documentaries, you'll see herds of animals and there'll be a predator, make it a lion, and the lions are walking closer and closer and closer to the herds, and the herds aren't worried at all. They're doing this math in their head, instinctively. And then all of a sudden you'll see a few of the heads of the zebras go up and look at the lions, and you can see they're going, and then all of a sudden the whole herd knows, okay, this is the point where if I don't start running, I'm lunch. It's a relative velocity question. There's another factor involved. Typically, prey animals, like zebras, can run for longer than predator animals. Often the predator animals can run faster, but in short bursts. And so there's the whole, how long can the predator run before it gets tired? It's a little dance that goes on, but it involves this physics here, but instinctively. Basically, I'm saying, dudes, if zebras can do it, come on. Turn the page.
So you think they're like converting equations into science?
I think what's happening is the animals that don't have a good natural instinct for it get killed off and don't pass their genes on to the next generation. So over thousands, over hundreds of thousands, over millions of years, you gradually have a paranoid group of zebras, but also the zebras that are too paranoid, that run all the time, they waste energy and they end up starving themselves to death because they're always having to eat more than the other zebras to make up for it. And so their genes also don't get passed on. And so you end up with a herd that has a pretty good instinct. That's how the system works. It's really pretty cool. Airplanes are neat. Nick and Cole are having an argument at an airport on a windy day. Nick says airplanes should take off with the wind so that it's pushing them from behind, and that way the planes get a speed boost on the runway. Cole says that airplanes should take off into the wind. He's not really sure why, but it makes sense to him. Who is correct? Did they take off into the wind? Why? Why? Put your pencils down, look up.
So like if you were flying right side up, you would be going down.
Well, your controls are reversed, if that's what you're asking.
Yeah, but I mean, like, so I don't know how planes work and all that too well, but you have like flaps to control what your angle you're flying at. So would you want to just completely?
The flaps don't control what angle you're flying at. They affect something else, which affects something else, which affects what angle you're flying at. And so I'll answer your question better at the end of the lesson. But Cole is correct. What was the speed of the plane relative to the ground? I think we would safely say 0 meters per second. What was the speed of the plane relative to the wind? Takeoff speed. Yes? For the rest of this lesson, Brandon, we're going to concern ourselves with speed, not with velocity. So I don't care about forward, backward, negative, or positive. However, Cleo, what will the acceleration always be equal to? If we have two moving objects, that's all I'm going to expect you to handle. Okay. Example 4 says, state the relative speed in each case. In this first situation where you have two, let's call them cars, going at 40 kilometers per hour, relative to each other, how fast are they traveling? Go with the obvious answer, Owen. In the right-hand situation, where you have the back car going 40 and the front car going 20, how fast are they traveling relative to each other? 20. I don't care about the direction. 20. What's the relative speed in this third situation? What? Based on that, So first of all, let's write that. What would cause more damage in a car accident, getting rear-ended or having a head-on collision? Why are head-on collisions worse? Because the relative speed is higher. Okay. I like example 5, I like example 5, I like example 5. Example 5 is a nice question. How long does it take these trains to completely pass each other? Looking at the picture, do I have more than one object moving? Are they moving at different speeds? This is a job for relative speed. What's A going to be, Cleo? Okay. This is a tough question to do if you analyze them both individually. You can, by the way. It would end up being a system of equations. So last year in Math 10, you learned how to solve two equations with x's and y's at the same time. You would set up two equations with t's and d's at the same time, and then you would let each one equal d, and you would let them equal each other, and you would substitute one equation into the... It's doable, but a much better way is to pretend that this front train is standing still and just use relative speed. Davis, what's this question asking me to find when it says how long? What's the relative speed between these two trains? I'll give you a hint. It's neither 13 nor 5. 8. Yep. It's a good habit just to remind yourself that A is 0. It's all of writing 3 letters, and it reminds you that there's 2 objects, and it reminds you that your final answer, you'll see later, is not your final answer yet. I'll show you what I mean for a tougher question. What's the distance? I'm going to argue that for the train to pass the front train, the back end has to get all the way past the front end. I think that's what we mean by pass each other. How far will the back end have to travel? Now, I realize they're both moving forwards. Who cares? That's relative to the Earth. We don't care about that. We're just comparing relative to each other. How far does the back train have to travel to pass the front train? How much? Yeah. See it? So again, now I would use D equals VIT plus a half A. Oh, what's A? So I would use D equals VIT. Wait a minute. Since A is 0, VI is just going to be VR. It's going to be VF. You know what? No. Do we have 2 objects moving? VREL. I'm going to use D equals that. How would you get the T by itself? How would you get the T by itself? More specific, divide what? Divide the V over. So it's going to be 250 divided by 8. 30 something, 32, 31 point something. 32 point something? 31.25? Oh, sorry, the distance that we're using between them? Yeah, we don't care about the Earth. We're just caring about these trains, and so we're pretending that this front train is at rest, and this back train is traveling at 8 meters per second, and it's only going to have to travel 250 meters. That time will be accurate, even though everything is moving forwards. Who cares about that? Yeah. You get something similar if you're walking on a moving walkway at an airport. As you hurry to catch your flight at the local airport, you encounter a moving walkway that is 85 meters long and has a speed of 2.2 meters per second relative to the ground. If it takes you 68 seconds to cover 85 meters when walking on the ground at a constant speed, what's your walking speed? Okay, this is not on the actual sidewalk yet. I just like to know how fast you walk. Constant speed, what's A? 0. So I think we can use this. Figured out where we are? Okay. I want to get the V by itself. Aiden, how would I get the V by itself? Sorry? Divide by T? Yeah. Oh, yeah. You said drop the D down and divide by T. Yes. So this is my walking speed. Oh, you know what? That works, because look at the units. It would be meters over seconds, which is meters per second, which is a speed. It's going to be 85 meters in 68 seconds. How fast do I walk? I think I made this work out to a nice digit, didn't I not? I think. 1.25? Even, right? It stops. That's about right for an average person. Okay. Now we're going to get on the walkway. How long will it take me to cover that 85 meters if I use the walkway? Well, it's still asking me to find time. The distance is still 85, but now I'm going to use my relative speed. How fast am I traveling relative to the ground once I'm on the walkway? In our notes, I'll write 2.2 plus 1.25. In your homework, if you just write 3.45, I'm fine with that, but this way we know where the heck we got that. Well, again, A is 0, D is V times T. So I guess T is going to be D over my relative speed to the ground. It's going to be 85 divided by 3.45. I doubt this will work out evenly. I get 24.6 seconds. Is that correct? How long did it take me originally without the walkway? How long did it take me with the... How much time did I save? Do the numbers. Do the math. You got calculators. How much time did I save? How much? That's airport gold right there. Like, please don't be dumb and think the airports built those walkways because you're tired and they're, oh, you're so tired and we don't want you to have to. The longer you're at the airport, the more money the airports are losing. When do airports make money? Once you're in the air. That's when they're making their money. And so if they can get a few hundred passengers to their gates that much quicker, we can launch that many more planes per hour. That's money in the bank. But don't ever think, oh, they built those walkways because they were taking pity on us poor travelers. If they were taking pity on you, you'd have leg room on those planes, right? Do you have leg room on modern airplanes? And is it getting less and less every year? And you're at a bad situation right now, you folks, because your bodies are still growing, so your bodies are getting bigger, and the plane legroom is getting less. So your next few flights, until your growth kind of finally settles down, it's always going to be, what the heck is going on here? So, how many of you have been to Las Vegas before? They have moving walkways there too. Is it because they took pity on you and you're tired? They have walkways going across the strip to help you cross the road? Is that because, oh, you're so tired? No. They're losing money if you're not in the buildings. They're only making money if you're in the casino. Let's get you out of the street into the casino as soon as we can. B. How many of you have done this? Walked in the wrong direction on the walkways. Okay? Try it. If you're at an airport and it's late, so you're not being an idiot and affecting traffic, if the walkway isn't crowded, I'm dead serious. There's some lovely physics going on here. So suppose you get on the walkway, but you turn around and you start walking in the opposite direction, so it sort of looks like you're moonwalking. You're facing backwards, moving forwards. And like me, you're stubborn. You're going to commit this all the way to the end. So the entire 85 meters, you're going to be walking towards the back while moving forwards. What will your new speed be relative to the ground, first of all?
Or just a trend.
Well, but I want you to go somewhere. We need a distance here. What will your new speed be? What's your relative speed now? I'll give you a hint. I don't think it's 3.45. How'd you get that? How long will it take you now? You know what? I notice we have a lovely equation for time sitting right here, Cleo. See it, see it, see it? So let's be lazy and just go, well, T equals D over V rel. This is why, Carter, I said I like to write the rel. It reminds me which velocity I'm using it, or which speed I'm using at this particular point in time. It's going to be 85 divided by 0.95. How long will it take? A little more than 85 seconds, I can tell you that. 89.4? Okay. Those moving walkways have some lovely relative velocity physics. They really do. Also, if you dive into some of the YouTube videos, you'll see people have had a lot of fun on those walkways, coming up with clever ways to make little movies or whatever on them. Yes? Quick look at money. Before you go, I like example 4. I like example 4. Example 4 is a nice question. Example 4 is going to be on your test because, hey, it's cops and robbers, but also there's some lovely physics. And this also explains a little bit of the physics behind how police radar detectors work. When a police car is driving towards you and the police officer uses his radar detector to see how fast you're traveling, are there two objects moving at different speeds? That's a job for relative speed. The police are in hot pursuit of a car. The car is 320 meters ahead. The car is going 150 kilometers per hour. The police want to ram the car in 20 seconds. How fast must they go in kilometers per hour? Noah, what's this question asking me to find? How what? Okay. Their velocity. Is there more than one object? Are they moving at different speeds? This is a job for relative speed. So even though you said velocity, I'm going to find... I can't hear you. Because if they weren't, how would the police catch up? I'm gonna, don't take this wrong, but I'm gonna say I hope that's a bit of a Captain Obvious now that you're thinking, oh yeah, if they're going at the same speed, they're not catching up in 20 seconds. Okay. What's that 320? Yeah. All right, sorry, why did I write 20? 320. What's that 20? Time. What's A, Cleo? Because there's more than one object moving at different speeds. What's that 150? Ignore it. Here's what we're going to do first. Just like we did with the train question, we're going to pretend the bad guys are standing still. We're going to figure out how fast we need to be traveling relative to the bad guys to catch them in 20 seconds. Then we'll take into account that the bad guys aren't standing still. So we're going to again use D equals VREL T plus a half A. Oh, no, A is 0. So D equals VT. Pardon me? V relative equals D over T. So it's going to be 320 over 20. If the bad guys are standing still, how fast do the police need to be going? Is it 16? Units? Meters per second? How fast are the bad guys going? So the police have to be going 16 meters per second faster than 150 kilometers per hour. Oh, I can't do that. What do I need to do with this 16 first? Convert it to kilometers per hour. Something to do with a 3.6. Is it times or is it divide? So V rel is going to be 16 times 3.6. What'd you get, Austin? That's the relative speed. The police is going to be, well, the bad guys are going 150. The police have to be going 57.6 kilometers per hour faster. I can do that in my head. 207.6 kilometers per hour. This right here is also much of the physics self-driving cars are going to have to be doing, but instead to avoid hitting each other instead of figuring out how to hit each other. This also, if you give me this number, this 207, I can work my way backwards and figure out how fast the bad guys must have been traveling. I can get that 150. That's what radar detectors that are mounted in moving police cars are doing. Okay. So there's some lovely physics there. I'm going to tell you which, we have a summary. I forgot to include this in your lesson. I had photocopied it already, but this is worth adding to the bottom of this page. Short summary. You know what? I would write this. Summary. Write that. And then skip where it says short version to calculate. Start with the word if they are traveling in the same direction. How do you calculate the relative speed if one vehicle is going forward at 60 and the other vehicle is going forward at 100? What is the relative speed between the two of them? If one vehicle is going forward at 60, the other one's going forward at 100, what's the relative speed? Is it 160 or is it 40? How do you find it? Bigger minus smaller. What if they're traveling in opposite directions, like a head-on collision toward each other? Or if they're heading away from each other, what do you do with the two speeds? Subtract them? So I would also jot that down. I'd already photocopied your lesson, sorry, and then I thought, I should have done a nice little summary, because that's really what we were doing. If you're asking, how are we figuring out the relative speed? We don't care about direction. I said to you, I did direction because I wanted to at least explain it, but we're really going to care about relative speeds. If they're going towards each other or away from each other, add them up. If they're going in the same direction, the relative speed is bigger minus smaller. Okay. Your homework. You're also going to get an entire week to work on this. I'm going to throw a fair chunk at you. For your homework, cross out number 3. Sadly, that's the only one you're crossing out. Okay? Try the rest. But I got a couple of cool videos to show you first. Put your pencils down.